Okay, good, very good. So today let's continue to talk about the direct method, and let's go through the steps carefully. And I hope you all of you master this important fundamental skills. Okay, and then in the exam and homeworks, make sure you use the knowledge we explained in the class to practice. Okay, and then make sure you can do it very, very precisely. Okay, very good. So let's get started. Okay, so far our class progress, the timing is excellent. So we are in the schedule and everything goes as we currently planned. That's good. So I think all of you are doing well with us. And then please keep up your great work. And then we move on to different sections, and then you will learn more and more important fundamental element knowledge. Okay. Very good, very good. So before today's class, let's talk a little bit about the logistics. Can all of you hear me? Yeah, yeah. Okay, very good, very good. Yeah. Make sure unmute yourself when you join. Okay. So but when you have a question, ask directly. You can shout out, unmute yourself, shout out, or you can type in the chat. I will monitor the chat from time to time. So make sure you do that. Okay. So we can solve your any confusion, any answer your any question on spot in the class. Okay. Very good. So a little bit update of logistics. So as I said, homework 0 and homework number 1 are used for your practice. So you can use them to find out whether you still have any knowledge holes, and whether you can do those exercises independently. Okay, so use them as the opportunities for you to practice. I uploaded the solution for homework number 1 already. You can use that to help yourself. Okay. Next Monday, September 19th, let's have the first quiz. So this quiz will be on the direct method we have discussed. So make sure you understand all the materials we discussed in the class. Make sure you can do it by yourself in a quick way. Okay. So quiz question will not be very difficult, but very fundamental, key to the concept. So you can use once you understand all the concepts, and then if you go through the example we discussed in the class carefully, then you should be fine. You should have zero problem. Make sure that you follow my suggestion, and also remember 5 times policy, right? We mentioned the 5 times policy that Professor Mark Shablick recommended. So 5 times you review those materials, then your brain will be strengthened. Then you understand those things better. Okay, so quiz should be no problem for you. I uploaded a quiz example that is for mathematics. So our quiz 1 will be direct method. So we will have a 1D spring connected simple format. So you can go through the examples we discussed in the class. Then once you can do that, then should be okay. Okay. So that's the quiz 1. We also will have our midterm exam number 1 on Wednesday. So this exam will be 2 or 3 major problems, and then we'll cover all the materials we discussed so far. So as long as you follow up the class, you do the exercises, practice, then it should be okay. Okay, so don't worry about the exam. Use this opportunity for you to find out whether you have any concepts still not thoroughly understood. Okay, so use that.
Are the exams and quizzes during class and on honor lock, or in person?
In person. So we will have the quiz and the exam showing in the shared screen, just like we're in the class. I will show the exam and the quiz exam sheet on the screen, and then you guys can start to work on that during the class. The quiz will be 10 to 15 minutes. So at the end of the class, quiz, and then once you finish that, you just email to the TA, or send it to the, I think it's email to TA is better. So you can email to him. I will put his email address here, and then exam will be the whole class. Yeah, please.
So, Professor, so like that means the quiz is pretty much going to be on Zoom conference like we are in class right now.
In class. Yes. Yes.
Okay. Is the exam like that too, or do we
Yes.
have to go in
Yes.
class? Okay,
Both.
understood. Thank you.
Very good. Very good question. Yeah. Please shout out if you have any questions so that all the classmates will be on the same page. That's excellent. So I saw a question. Will exam one including trust element in addition to direct method and the metrics? No, no. The exam one will only cover all the materials we have discussed so far. So all the materials we have explained in details are the ones you need to master so that you can do well in the exam. So no worry about the additional material. Okay, just focus on the knowledge we discussed in the class. Yeah, very good question. Very good. So let's clarify many things. It should be online. Exam is online. Yeah, Emil, can you hear me? Emil, during
yeah, I can hear you.
Yeah, during the class time, as I just explained. Yeah. Mm-hmm.
Okay, so when it would start like at 12:45?
12:50.
12:50. Okay.
Yeah.
All right. Thank you.
Excellent. Very good. You guys are all asking very good questions. So this clarify many things. That's excellent. Any other questions? Any other questions? Yeah, please feel free to ask me if you have when a question arise. Okay. Yeah. Very good. So can you guys see my shared screen, the slides? Yeah, excellent. Good. So the final two items about the logistics is the epic tutorial videos. So you will watch those tutorial videos on those 3 days. We will not have class. So, but you can watch that during the class time. We will not meet on the Zoom. So you will use you will watch these 3 videos respectively on these 3 days. And then I have the PowerPoint slides also uploaded. You can use that to review the material. Okay. After that, after the end of September, we will replace those 3 videos with 2 new videos. That's the EPICS tutorial number 4 and number 5. So make sure you keep a copy of all the videos. And then on September 26th, we will have an in-person lecture. That's given by the guest lecturer, Professor Feng from ECE. Okay, so it will be great that all of us join the classroom, go to the classroom together. Okay, that will be great. Also, we have four more invited speakers. They will give us a nice introduction of their research relevant to computational mechanics, finite element. That will be excellent. Some of them will be in person. Some of them will be online. I will give you the heads up before that. Okay, so those are excellent lectures that will help you to expand your horizon to understand the field better. But in the class, in our own lectures, we will dig into finite element and give a very thorough study, and let all of you have a solid master of all those important finite element knowledges. Okay, so we will balance those well. Yeah, so very good, very good. Any questions regarding to logistics? And here is the plan, current plan for the September. Okay, very good. Can you guys hear me? Yeah, excellent, excellent. Okay, very good. So you can hear me and you can see the shared slides. Very good. So good. Okay, so yeah, also the survey. Many of you, that's really great. And many of you send me the survey and very positive suggestions, very positive comments. So from all those positive, constructive comments, it seems that you guys are doing very well. You are learning in the class and find the class are interesting. That's good. That's very good. I hope you feel interesting and also learn things from the class material. Okay, and then this will benefit your future career. That's really great. And if you have any suggestions to make the class even better, yeah, let me know, email me, okay? So then we can modify the class to help all of you. Yeah, that is the win-win scenario. That's the best, okay? Yeah, good. Oh, I have a question here. Will we have a practice exam and a practice quiz? So we may not have, Sarah asked this question. So we may not have time for practice exam. I put the practice quiz question, mathematical quiz question online, and the new quiz question asked in the new quiz will be different. So, but the style will be the same. You can see how straightforward will be the quiz question. Okay. So, and for the exam question, they will be less comprehensive than homework, but more comprehensive than quiz. So if you are able to do the homework problems independently, you will have no question on the exam. It'll be all fine. Okay. Sarah, can you hear me? Sarah. Yeah, excellent, excellent. Very good question. Very good. Yeah. Okay. Ask me if you guys have more questions. Okay. So I'm now, let's go to the material that we have discussed. Let's briefly review what we have learned, and then we get to the new material today. Okay. Okay. So we talked about the direct method. Okay. And this method is a fundamental in the finite element and super important. Okay. So we have seen this 1D system of the spring, and we have get familiar with the notation of the node, which consists of wall and the rigid movable body, right? This is a notation, number enclosed by circle. And then we get familiar with the notation of element. That is a spring here. There's element, right? So they are just use the number to denote that, right? Spring and the wall and the rigid body are connected together, solidly connected together. Wall cannot move, rigid body can move. And also external force can be applied to rigid body. And here some definition you need to be very, very familiar with is wall cannot be deformed. They can only sustain force, generate reaction force. So there's no displacement on the wall. Okay, that's the wall. For the rigid movable body, we also call it a node. It can move. It can have displacement. It can also sustain the force applied by the spring, as well as the external force applied. So external force is used capital F to denote it. Okay, and the force coming from the spring, we use a small f to denote that. Okay, for the spring, it can deform. It can have the elongation, but it cannot sustain external force applied to it. External force always applied to the rigid body, and then through a rigid body, they connect to the spring. Spring will generate the force there. Okay, so these are the key definition, key idealization of the system, of the different components of the system. Okay, so you need to be very, very clear about this. So whenever you see this 1D system of spring, you will know the property of the wall, property of this rigid body, movable rigid body, and the properties of springs. Okay, so you need to know this. And those springs are called element. The rigid body, either movable or non-movable, they are called node. Okay, so those are super important concepts. Can you guys hear me and see my moving cursor? Can you hear me? Yeah, yeah. Okay, very good, very good. Now, we also discussed about the connectivity table, right? So this is a very important table that you need to generate when you are working on the 1D spring system. Okay, so the convention for this is from left to right, from node number left to the node number right, and then you form the column that has the element number, the left node number of element, and the right element of the element. Here we only talk about the spring, right? 1D spring. So every spring will have only two nodes, right? and from left to right, you can feed that in to the table. And that the column means the element node. Row means the element identity, element 1 to element 6 in this case. Okay, so once you have this formed, this table formed, then next step you can easily write the individual matrix as well as the global matrix. Okay, so before you write individual matrix, you also need to know the convention of how we describe each spring. So each spring we write the node here, like this generic spring. We have I enclosed with circle I, node J for the spring E, right? And then on this, as I said, this spring cannot sustain any external force. You cannot apply force to a spring, but force can be applied on the movable rigid body, and then that will be connected with the node. Means on the node you can have force. Okay, and this force will be in equilibrium with the force generated by the spring. So then in this case, we can generically denote that on the two nodes of this spring E, we have two force applied. One is called force I, subscript I, means applied on the node I. And then with superscript E in the parentheses, that means that we are talking about the spring E, right? So FIE, that is for the node I. For the node J, you have FJE that apply to the node J. Okay, you have these two. And then you on the node, you also have displacement, UI, UJ. Okay, so that describe this four different parameters describe the mechanical state of the spring. There's one more parameter very important for the spring is the material parameter of the spring. So you also will get the spring constant of the spring, that is called Ke, which is showing here. You see my moving cursor. Yeah, excellent, Sean. Very good, Sean. So you see this. So these 5 parameters together, you will know the complete information of this spring, of this element. Okay. Now, because we are dealing with a static condition in this class, so for this spring, we can regard it as an individual body. Within this individual body, forces are in equilibrium. In this case, the two forces we identified, FIE, FJE, they can be added together. They added together that equal to 0. Means FIE equals to minus FJE. Okay? So this is super important. Many students will need some time to get familiar with this process. So I hope you to think through this process. Then you will not make a slight error during the computation. Okay. So this is from the force equilibrium. And because this spring will generate its own force to balance with external force. So the force the spring generator equals to the spring constant times deformation of the spring. That is Ke times Uj minus Ui. Here Uj minus Ui is from here, Uj minus Ui. That gives the deformation of the spring. Okay, so I have explained that before. Now it gives the force P equals to Ke Uj minus Ui. Because here is Uj minus Ui, that means we are using J node, using the J node as a reference. So on this node, this force should, the P force generated should be in balance with the external force applied on this node, which is the FJE. Okay, so that's why FJE equals to PE. You can this can be also done in the node I. If you take a look at the node I, then the force on the node I is Ke Ui minus Uj. And then the force they are balancing with Fi is actually inverse sign. Okay, inverse sign. This all these things are self-consistent. When you get familiar with it, you will find the false and the false, they're actually all very consistent. Okay. So overall, it means we have the full information of this spring now. Some parameters are known, some are not known. That, and for the unknown things, we are going to solve that. For the known things, we will put that into the equation and then use that to combine with the other equation from other spring, because we have a system, right? Not only one spring, many spring. We will put them together and then solve the whole equation set. Okay. So, and we have discussed about for any one spring, you can write the force, as I mentioned before, the force on the node I is Fi, because we use I as a reference. So Fi equals to K Ui minus Uj. For the force J, we use J as a reference. Then Fj is K Uj minus Ui. And then we reverse this this order just because we want to write this into the matrix form, right? So we have we extract U out, the Ui and the Uj, that it is a vector. And then we have the remaining part written in the 2 by 2 matrix, and then multiply them together equals to another vector Fi and Fj. Okay, so eventually you can also make it then into a abbreviation form. Dedicated K U equal to F. K Q. U can also be written as Q, because Q is more generic. It's called the vector of degree of freedom. If we have this is only 1D case. If for 2D, 3D case, we have Vi, Vj, Wi, Wj. Then we have a Q is the 6 by 1 vectors. Okay, so then K times Q equal to F, right? So, and you can also write it in a very abbreviated form. K bold dot Q bold equal to F bold, right? So this is the convention that you need to get very familiar with, how to calculate, how to form this kind of equation set for the single spring. And then in last class, we also talked about what's the properties of this equation of this matrix, right? So we mentioned that this matrix is it is a square matrix. It relates to the same number of force with the same number of displacement, right? For this case, we only have 2 numbers of force, 2 number of displacement on 2 nodes, right? If you have a 6, means if you have X, Y, Z, 3 different directions, you have 6 numbers of force, 6 number of displacement on the 2 nodes, right? Every node has X, Y, Z, right? So that actually is, we will explain that in the truss structure, okay? And this matrix is symmetric, singular, and positive or semi-definite, okay? Can you guys hear me? Yeah, excellent. Let me very briefly go through this material, and then we get into a new material today. Okay, so here we also discussed about the observations that when we form this equation, if we have displacement null, then with that we can calculate the force directly. But if we don't have displacement, we're only given the node force, then we cannot calculate displacement uniquely, because this K is singular. So the equation, these 2 equations we showed here, these two equations, they are not independent, because if you add a minus sign to it, and then plus the another equation, they equal to 0, because these 2 equations are dependent to each other, because they are coming from same spring. The force is in equilibrium. If you have more spring connected together, then the matrix will not be singular. Then you can get a unique solution. Okay. And in last class, we started to analyze the multi-spring systems, right? So we have gone through this process. We have those different equations, different springs, and then you can practice how to write the connectivity map for this system, for each element. The element is a spring. Okay. Now from here, from the connectivity map, you will find you have 6 elements. You have 6 elements and 5 nodes. You have 5 nodes. Okay. 5 nodes means you have this is a 1D system. So 5 nodes means you have a 5 force. Okay, 5 force. On 5, I mean the force is summed together. In fact, you have a 5 displacement. On each displacement, on each node, you have many force there, and then summarized together to be one force. Okay, so here you have five number of displacement. Then the equation you will generate here will be a 5 by 5 matrix and 5 by 1 displacement vector, 5 by 1 force vector. So you will generate this format. Once you have this format, you can add the individual matrix of each element into it. We have 6 elements, so you will add 6 times for each element into this equation, into their corresponding position. Okay. For the equation, for the element number 1, this one, we can write it K1 minus K1 minus K1 K1 and U1 U2 because it has the element. It has element 1 and node 1, node 2. So we have U1 U2, F1 F2. You see the 1 in the parentheses are in the superscript. That means we're talking about the string number 1, right? So when you write this, you can add that into this format. You have a K1 minus K1 minus K1 K1 in this 1 2 position, column 1 column 2, row 1 row 2, because they are corresponding to U1 U2 F1 F2. Okay, do you guys follow me? Yeah, okay, very good, very good. I want to make sure this is super clear, so then you have no trouble at all in understanding how to do that. But after my explanation, it's better you repeat it one time in your own hand to do it by yourself, and then check with the solution in the slides. Okay. Now this is the for element number 1. We put it into this equation now. We can do the same thing for element number 2. Remember here, element number 2 connected to the node 2, node 4. So element number 2, string number 2, connected to the node 2, node 4. Then you write this equation, right? So make sure all the notation are no mistake. And then you add this into this equation. This blue one element number 2, right? So they will be in the column 2, column 4, row 2, row 4. Okay, and then you have an additional force added because displacement are shared by the node. Every node has only one displacement, but it can have multiple sources to receive the force. Some of the force are coming from the connected springs. Some are coming from the external applied force, right? So you start to add the force together on the right hand side. Add the spring constant into the matrix at the left hand side, but keep the displacement all the same. And those displacement, most of them are unknown. So you keep the displacement there. Now, we repeat for the same thing for the element number 3. So based on the connectivity map, you know how to write those notations here, right? And then you add it into this format. You have a red one. They are element number 3. And then we repeat it. Element number 4, purple color. And then you see force are added on the right hand side. And then element number 5, that's green color. Okay, so you add this into the matrix. And then finally, element number 6, you have this more than brown color. Number 6, you add that into the matrix. So now, up to now, we have a global matrix generated, and then the displacement vector remain here, and we have a global force vector generated. So here, those are the force generated and applied by the spring on the node collectively on each node. Okay, so you can actually test from here, from top to right, top to down. They are the node number 1 to node number 5. You can see node number 1, there are 2 components. That means on node number 1, there should be 2 connections here. So see, node number 1 is the wall. It has the 2 spring connected, number 1, number 4. So that's why we have 2 force, F1, 1, F1, 4. Node number 2, this one, it has 3 connections, 1, 2, 3. So it has 3 force applied by the spring, okay, by the spring. But of course, this force, we also have an external force applied. So here we have not considered that yet, because we only now consider how the spring are used, to cause force based on their deformation, right? So and so on, 3, 4, 5. You can find out you can check the number here to find out whether you did it correctly or not. After that, we use the force equilibrium condition. We start to use the force equilibrium condition. Now, as I said, on each point, we will have force applied, force generated in the spring, right? We have force generated in the spring. This force generated in the spring will be balanced by the force applied to the node. These two forces are in inverse sign because they cancel each other. So by adding all the force generated by the spring together and then add a minus sign to it, it actually gives the force applied by all the spring on this node. That force should be in balance with any external applied force. So here, for each node, we can say node I, each node, we can write it in that format. We can write the external force applied to a node plus the minus of all the force generated in the spring, okay, all generated in the spring. So that means the Fi minus, because plus and minus is minus that all the force generated on by the spring, and on that node, that equal to 0, okay. So this is generic for any node. Then we can move the summary of this force to the right hand side. That means Fi, the external force, equals to all the internal force added together. Here, the force the I means in the node I, because we are talking about the node on the specific node I, right? And the E is a spring. On that node, there are multiple springs. This E is from R1 to IE. This IE actually is ND node, the spring number. No, IE is the spring number, and this I is the node number for every node. Okay, so once you understand this, then for example, for the node number 3 in current case, node number 3, this one, you have spring number 3 apply a force F3. Spring number 4 have a force F3 on the node number 3. You have a spring applied through the force applied by spring 5, F3, and you have the external force F3. So all 4 forces applied to the node number 3 get balanced. They get balanced, and you can write it as F3 minus F33 minus F34 minus F35 equal to 0. So go ahead after the class. Go ahead to practice it, understand it. You will if you understand what I talked about here, the definition about the force on the spring, and then you go through this process, understand this process, then you can write this one. So this equation is valid. This equation also tells us that like this one also tells us all the force summarized together from different spring added together equals to external force. That means in the equation we just showed here, we assembled a global equation. On the right hand side, once we add all these force together from spring, if we did it correctly, then each one actually can be replaced by the external force. So this one, F1 on the node number 1, F11 plus F14, they actually equal to the external force. That external force on this one is the reaction force generated by the wall. The wall will generate a reaction force, right? So that we use reaction force, we usually use capital R to denote it. So this is the capital R1, capital R1. Okay? Here you see it's not a bolded, it's not a bolded form. That means that this is a scalar, it's a number, no direction. And then for the number two node, you have 3 force added together from 3 springs. And then they should equal to the external force applied to number 2. For this case, that is F2, right? F2 here. Same thing for the node 3, that's F3. Node number 4, F4. Node number 5, which is a wall, that is R5, reaction force by the wall, right? So this give this format based on this force equilibrium. It converts internal condition into the external condition. So then when we consider this whole system, you don't need to worry about the internal force anymore. You just worry about what's the external force there, and then add the external force into this column, right? So then our equation change to this format. We have the K assembled here. This K is actually called global structure stiffness matrix. You have this system, this matrix times all the displacement of all the nodes, and then equals to all the external force applied to the nodes, right? So this is a beautiful format, and this format can be rewrite as the KQ times F. Here you see K is all of them we write as the capital now, because now we are looking at a global format, not the local, global, right? KQ, Q is the degree of freedom, F is the force, and S also, yeah, and S is called the system. This is the whole system. And for this matrix, for this assembled global matrix, is actually square, symmetrical, singular, and positive or semi-definite. This is a key properties. You need to have that in mind. Make sure you understand every term. What does that mean? In an exam, we can give you some questions to ask you explain the terminologies. So you need to quickly explain what's those different terms mean. Okay, so that's very important. Can you guys hear me? Can you guys hear me? Yeah. Okay. If you want me to explain faster or slower, let me know. Okay, I can always do that. So don't be shy. Just shout out. Okay. So far, I'm using the pace that most of you actually said is very good. So I use this pace. But if you want me to adjust it, that's totally fine. Okay, let me know. Good. So now we want to solve this equation set, right? So let's look into that carefully. So in this case, we have 2 walls. So on the wall, as we said, they cannot move. So the displacement equal to 0. U1, U5 equal to 0. So this one 0, this one 0. R1 and R2 are unknown. We want to find that out, right? So we want to find that out, right? So we can go ahead to use that. We can go ahead to solve that. Here we have an alternative, another slide. You can see there's an alternative way. So there's an alternative way to assemble this equation set. There's another way. You can also use that. Okay. So let me briefly explain to you how to do that alternatively. So this alternative way actually is coming. We can go directly from the force equilibrium first, rather than the 2x2 matrix of individual spring, okay, and then assemble them together. That's the way we have gone through today. But there's a different way. Different ways you go backwards. You firstly from the force equilibrium, you know Fi equal to the external force equal to the individual spring force together into the added together sum, right? From there, you can write F1 equal to F1 at 1 plus F4 1. That's for the node number 1 here, right? You have this. So F11 actually is K1 U1 minus U2. Always because you are talking about the node 1. So then always use this 1 that connect with spring as a reference. And when you use this as reference, then is this number, this point with respect to another point, with the opposite point. So in this case, the force on the spring 1 is the K1 times U1 minus U2. Okay, that's the force on that node 1 of the spring. And then for the spring number 4, this one, we have a K4 times U1 minus U3 because it connected to the node number 3 for the spring number 4, right? So K4 U1 minus U3. Then we have one equation: force, external force, and the displacement of the node. For the force number 2, which is here, we already know force number 2 should equal to the sum of 3 force generated by the spring, right? So we can write it F2 equal to F21 plus F23 plus F22, because those are 3 different springs connected to the node number 2. Then you can also write it K1 U2 minus U1 plus K3 U2 minus U3 plus K2 U2 minus U4. Remember, all of them are starting with U2 because we are dealing with node 2. Okay, so you can write it this way. Now, follow the same procedure. You write F3, F4, F5. All the nodes, your force, you can be write this way. Once you write it this way, you can see force is given here, and they are all the displacement given. Then you can sort out the displacement. You can write it in terms of U1, U2, U3, U4, U5. And here, in this case, U3, U4, and U5 equal to 0 for the first equation. And the others they have. And then extract all the displacement. Let it form a vector. And the remaining part, the K, should be a 5 by 5 matrix. Right? We have practiced before, mathematical operations. This is a 5 by 5 matrix. This matrix will be the same as this one. It will be the same. Okay, we are just using different rules to calculate this equation set. So you can practice it after class, see whether from here you can get the same K or not. Okay. Now, by those two means, we will get this equation set here, expressed by the matrix and the vector. Now we start to solve it, okay, by using the boundary conditions. So here, this is the equation we get. The boundary conditions will be the external force applied, that we know the number. External displacement boundary condition, that is on the wall, we know displacement equal to 0. So those are the information we know on the system. So we will impose those information as boundary conditions to solve the equation set. The way to do it is we will ignore the equation for which the right-hand side force are unknown. We will ignore those first. Here, if their right-hand side force are unknown, that means the left-hand side displacement is known, because we explained it that the force and displacement, when you solve the problem, they cannot be given at the same time. If they given at the same time, they can cause some trouble in the equation. So only one is known. From that, you can calculate the other. Okay, but usually what we do is we will have unknown. We will have unknown on the left-hand side. Okay, known on the right-hand side. So if they are unknown on the right-hand side, let's cross it out for now, and then get back to it in the next stage. Okay, so here the right-hand side force are unknown, and then we can struck out that. Okay, so this one we can struck out these two. Do you guys see my screen and see my mouse? Yeah, excellent. Follow me. Okay, yeah, very good. So now we can extract that. We can eliminate these two. Right? Once these two are eliminated, then we can also those rows are eliminated. We can also eliminate the columns in here, because this column will never. Usually, when you calculate this U1 will times the first column, right? But since we eliminated the U1 now, then it will have nothing to multiply with. So then we can eliminate these columns first, columns as well, right? So these two columns also get eliminated. So now in this equation, we have what left is a 3 by 3 matrix, 3 by 3 matrix, and then times a 3 by 1 vector equal to a 3 by 1 vector here, right? We have this. all the spring constant unknown, the displacement unknown, force unknown, external force, you know how big is the force applied. Then we have this kind of equation. So this equation, this is called global matrix equation. This equation, okay, KQ equal to F. Here, you see no S subscript now because this is not a system. This is a subsystem, part of it, right? And then here, the K, we usually call it global stiffness matrix K. K usually call this. And this matrix actually is the square symmetric. It has a square symmetric property, and it is a positive definite, and it is not singular. This one is not a singular. You can prove it. It's not a singular. When you multiply things together here, because you see here the K2, K5, K6, they will not be cancelled when you add the different equations together by adding the inverse sign. They will cannot cancel. They are independent the three equations now. Okay, from there, if they are not singular, then it has a non-zero determinant. Non-zero in that case, you can find the inverse of this matrix, right? We mentioned it in the mathematics class. So you can multiply K inverse, K minus 1 to both sides. K minus 1 times K equal to identity matrix I. You only have Q left here. But on the right-hand side, you have K minus 1 times F. And we already discussed about how to get the K minus 1 in the mathematics class, right? So you can use that. And then this K is null, F is null, force is null. Then this will give a matrix, give a one-dimensional matrix, which is the vector. That vector is the displacement. So from this displacement, you know the U2, U3, U4. You know that. And we already know what is U1 and U5 because they are zero. They are hooked to the wall, right? Then by all those displacement, if in this system, if I know all the displacement of the moving nodes, then I can back calculate the force in that spring, right? Because I know the spring constant of it. I know the displacement of this spring at both ends. Then I can use the Hooke's law to find out the force generated in this spring. I can do that now. And then once you know all the force in the spring, then they are all in a balance with the external force, right? So then you have all the mechanical parameters solved in the whole system. Displacement, force, right? So as I said, once you calculate all the displacement using this format, you use this displacement to calculate the deformation of the spring, and then combine with the spring constant, you get the force of the spring, right? And then from there, you can calculate you can check the force equilibrium. Then we get everything, right? Now, here is the example, quantitative example. From here, you can see how the problem can be quantitatively solved. Now, in this case, we let the F3 equal to 1000 Newton. F2 and F4 is 0. And then all the spring constant for the 6 elements, they are all given. We know they are spring constant. You remember the spring constant unit is Newton per millimeter. Okay, so those units are very important as well. You need to know you need to make them to be consistent. In the question, sometimes they give a Newton per centimeter, some give a Newton per meter. You need to make sure that they are all converted to a common unit. Then you can do the calculation between them. Okay, and then U1, U5 is 0. That we know. We know it's the wall displacement boundary condition. R1, R5 unknown reaction force. U2, U3, U4 unknown. The displacement of those moving unit we don't know. Okay, and then once we have that, you can put that into this equation now. Put the number. Then you will have this, all the number add in, unknown still remain in this form. Okay, and then you have unknown here, right? In next class we can do it together using the format I just discussed to solve this question, get the exact value of these 5 unknowns. Okay, right now it's 1:40. We can stop here and continue in next lecture. Yeah, very good. Excellent.
Professor, can I ask a question before you leave?